What's up, calculus students? Coming at you with the Unit 1, Lesson 2 homework. Um, gonna try to make sure what I didn't do for period 2, but what I did do for period 6, you understand the connection between Lesson 1 and this Lesson 2, because they're very much connected, and I think I was taking it for granted that you guys would see the connection um, in period 2, but many of you did not see the connection. So let's go and look at our first homework really quickly, and like perusing through this first homework, what were the interesting limit questions that I gave you? Okay, like for all of these questions, whether it's a graph or we have like a piecewise function, when we had a point wise function, we have these crazy things like where were the limit locations that I was asking you about? Well, they're always the interesting locations where we either don't have a function value, or we have like a jump, or we have, you know, a hole, and either there's nothing above or below the hole, or there is something above or below the hole. When we talked about piecewise functions, and I gave you this, what was the values that I really focused on? Well, when we left one piece and picked up the other piece. Here, like why did I pay attention to -1 and 2? Because it's possible locations of jumps. And then down here, like, why did I say find the limit as x approaches 3? Why didn't I pick different numbers? Because these were all locations of what's called discontinuities. Okay. And today's lesson and today's homework is really just the first day's homework, with one exception, really two. You have to tell me what the interesting limit locations would be. You have to evaluate those limits, and you have to figure out like what are the questions that I would have asked last class. That's essentially what day 2 is. With one exception, we're going to introduce the concept of a vertical asymptote. Okay, so like we are going to focus on the interesting locations. Now, here are the interesting locations from homework 1. They're locations where function values are undefined. There are locations where limits do not exist, or they don't agree with each other. And we remember from the first lesson that limits don't exist usually at jumps. Jumps occur at piecewise functions, or they occur at the jump function. Cool? When are function values undefined? Well, when we ever have answers that are like undefined is usually when we have zeros in the denominator. So like denominator is equal to 0. And we talked about in class, like what are the possibilities for a denominator with 0? Well, you could have 0 over 0, which is your indication of a hole. Now, new is like holes. We know that holes have limits. We want to find that limit, but we call holes removable. Okay. And then the other situation is we have numbers over zeros. Numbers over zeros, and we'll talk more about why, are locations of vertical asymptotes. We'll talk more about why next class. Now, vertical asymptotes are non-removable. The limit does not exist, and we can't really do anything to fix it. They're non-removable, and they're called infinite. Infinite discontinuities. Jumps are also non-removable. I'll just use NR, and that's it. So here's your situation. I'm going to give you a function. If it's just an expression, we should be thinking, oh, okay, these expressions, usually you'll have this or this. If it's a piecewise function or a pointwise function, you should be thinking to yourself, oh, piecewise functions, that's when we have like this or this. Okay. And that's how we kind of determine, what's the analysis we should do so we can figure out like the limits to find. So when are functions undefined or does not exist? Well, limits do not exist at jumps. We won't have jumps with just expressions like this. An expression like this we could have undefined function values. So really, again, it's just like day one. We want to evaluate limits with the extra step of you figure out the interesting numbers to try to find the limit of. So the extra step being figure out when the denominator is equal to 0. Figure out when your function's undefined. And we might as well factor everything, the top and the bottom. Cool. Just kind of like what we did last class is if I gave you something that could be factored, you usually want to factor it. Now be careful, like simplifying, but here's our first step. We find when the denominator equals 0. We got x equals 6. We got x equals -2. Okay, now you found the interesting locations that I would have asked you the limit questions about last class. So really, the rest is, what are the limits? What is the limit as x approaches 6 of this function? And what's the limit as x approaches -2 of this function? Now I'm writing all this out. You don't have to write all this out. You can kind of just like figure it out. And let's look at x approaches 6. Well, if I plug in numbers very, very close to 6, I'm going to get 6 times 8, or like a big number on the top. We're talking about a big number. I don't want to use this number symbol because I use it for stuff close to 0. But 6 times 8 is what? 48. But in the bottom, I'm going to get this number that's going to be close to 0 times this number close to 8. I'm going to end up with this like number over 0. This is an indication that the limit does not exist, that x equals 6 is a non-removable infinite discontinuity. It's the location of a vertical asymptote. Cool? So like numbers over 0 will approach infinities. We'll talk about that more next class. All you have to do is understand that, like, yeah, I can't cancel like that x minus 6. Or like, let's say you canceled the x plus 2s because you're like, if you're finding limits, you can cancel, which is true. You get 6 over 0. And 6 over 0, again, you can't evaluate, you can't reveal. Now over here, if you plug in a number close to -2, oh, this number will be close to 0, but it will be able to cancel with this number. You're going to get 0 over 0. 0 over 0 is an indication that we have a hole. After canceling that 0 over 0, you're left with -2 over -8, which is 1/4. Great. This is like, since you have a limit, you know you have a hole. Holes have limits. We know that x equals -2 is the location of a removable discontinuity. The location is at -2 1/4. You could say the limit as x approaches -2 was 1/4. They are both discontinuities. X equals -2 is a discontinuity. X equals 6 is a discontinuity. X equals -2 is the location of a hole. Here is the y coordinate location of the hole. X equals 6, vertical asymptote, not approaching either. So you see, like, it's like last class with one extra step and one extra thing to think about. Vertical asymptotes are new, and you have to find the interesting points or the discontinuities of the function that I would have asked you limit questions about. All right, next one, let's go ahead and factor a greatest common factor. Let's go ahead and factor a greatest common factor. Let's go ahead and factor again the two numbers that add to get 5 and multiply to get 6. Let's go ahead and factor the x plus 3, x minus 3. If I were to figure out interesting locations on this function where we could have a hole or an asymptote, figure out when I have a 0 in the denominator, we get 3 possible locations. Now let's think about evaluating or plugging in all 3 of these values or finding the limit. If I found the limit as x approaches 0, okay, well, when we're finding limits, we understand that you can essentially cancel terms that are equal to each other if you're plugging in values close to like 0. So if I'm plugging in 0, like, and for all the limits, I can cancel those. So for all of the limits, you could look at 2 times x plus 2 over x times x minus 3. If I plug in 0, I'll get 4 over 0 times negative 3. 4 over 0 is an indication that this is a vertical asymptote or a non-removable infinite discontinuity. Great. Now let's switch it to x equals negative 3. Well, I've already kind of removed the fact that if you plug in negative 3 or numbers close to negative 3, you'd have something here that would cancel with here that is close to 0. So those numbers are close to 0. Here, if I plug in negative 3, I get 2 times negative 1 over negative 3 times negative 6. This ends up being, this is 1/3. This is 1/9, positive negative 1/9. Oh, wait, I was allowed to plug a negative 3 into the simplified version, and I can plug it in close to here. Like if you plugged it into the original equation, you get 0 over 0. We have a hole. Since we do have this limit, we realize this must be a removable discontinuity, and the location is at negative 1/9. Hole. Because these dudes are literally just driving along on this lawnmower and like not doing anything. So I'm just going to leave this here as like the location. Removable, it's a hole. Removables are holes. Holes have locations. You looked at our last homework. Here's what holes look like. Don't have a point. It's 0 over 0. You do have a location. In 3, I get 2 times 5 over 3 times 0. We'd end up with a number over 0, which is an indication that we have this vertical asymptote or another non-removable infinite. I'm going to change up this one. All right, this is an interesting one because take the bottom set equal to 0. And I get 0 and negative 4. Now, like, when you're evaluating the limits, we can just essentially cancel the terms that are going to end up. Oh my god, I'm just some crazy noises going around here. You know that if you plug in something close to 0, this number is going to be close to 0. This number is going to be close to 4. This number is going to be close to 0. This number is going to be close to 4. It looks like all that stuff is going to cancel and you're just going to have 4. Or if you think about evaluating any kind of limit, you can remove like stuff that would end up canceling because you're never going to get 0 in the denominator. You're going to get something close to 0 when we're talking about plugging in something close to 0. So that could cancel, that could cancel. And I get that. We just get 4. Now, if I plug in 0, I get 4. If I plug in negative 4, I'm also going to get 4. So this is a situation where we have 2 removable discontinuities. They're both located at 4, which I'll write down in a second. Okay. We have a hole at 0, 4. We have a hole at negative 4, 4. And like, guys, you should be able to see this. If you go online and graph any of these equations, which we can always do, and I like to do occasionally just to like show that I've done stuff correctly. Like, let's take this first example. Let's graph x squared plus 2x and graph x squared minus 4x minus 12. Okay, we should see a hole at negative 2, 1/4. We should see an asymptote at 6. There is the asymptote at x equals 6, and here is a hole at negative 2, 1/4. So you can see at negative 2, we don't have a function value. This is beautiful to see. I should have done this a lot. But you can see that close to negative 2, we are close to the y coordinate of 0.25. Close to negative 2, close to the y coordinate of 0.25. So this is the location of the hole, negative 2, not undefined, negative 2, 1/4. Let's do that one. Well, let's just do the one that we just did, which is interesting because it looks like we should just be getting 4 all the time, but with a couple holes. Look at that. It's essentially y equals 4, but you can't plug in 0. There is a location of a discontinuity. We don't have a point. X equals 0 is a removable discontinuity. And also 4 is another location of the discontinuity. We have a hole at 4. Is it 4? It's x plus 4. Negative 4. There it is. So at negative 4, undefined, we don't have a point at negative 4. We have a discontinuity, but we have a location. We could take a point and replace it. I want you to do is take the bottom and set it equal to 0 for this one. I don't want you to stress about this one. It's just more keeping trigonometry in your brain. Don't lose trigonometry. Cosine equaling a half. Cosine is this adjacent, the horizontal distance. Which triangle is the adjacent of the horizontal? A half. That's going to be the tall 30, 60, 90 triangle. 60-degree base angle, pi over 3 radian measurement. Where is cosine positive? Cosine is positive in the first and in the fourth, so we want the pi over 3 in the first and the fourth quadrant. This is going to be at pi over 3 and 5 pi over 3, 6 pi over 3 minus a pi over 3. Okay. However, what's going on? Well, if you plugged in pi over 3 into the top and the bottom, I feel like I made a mistake and it should have been like pi over 3 minus pi over 3, or x minus pi over 3. You would get a number over 0. I don't know what the number is that you would get, but something over 0, something over 0. These are both non-removable infinite. These are both locations of vertical asymptotes. Cool? Cool. I'm about to change one and change this one. Skip this one. Sorry if you did it and you're checking your work. I'd like you to do a piecewise function. Close. Cool. We'll get to that one. Let's do this one first. Might as well factor x minus 7, x minus 2. But good question students have is like, what about x equals 7. We know x equals 2 makes the denominator equal to 0. What about x equals 7? Well, x equals 7 is easy. If you plug in 7, you get 0 over 5. 0 over 5 is 0. This is not a discontinuity. This is not an easy point. This is a boring point. If I ask you, what is the limit as x approaches 7 of this function? I hope you would plug in 7 and just be like, oh, 0 over 5. Okay, 0. This limit is 0. That's fine. We're allowed to have limits, and you're allowed to have zeros. What you're not allowed to have is a 0 in the denominator. So x equaling 2, that's bad. And if I ask you to find the limit as x approaches 2, well, again, you could cancel the x minus 2's. You're not allowed to plug in 2. We don't have a function value. If you plugged in 2, you get 0 over 0. If you plugged in 2 in the beginning, if you plugged in 2 into the factored part, we get 0 over 0. That is undefined. That is a location of a hole, but we can reveal its location, which is at -5. We found the limit. The limit is -5. So we know this is a removable discontinuity. That's its location. As we approach 2, we'll approach the y-coordinate of -5. Great. That kind of covers just expressions, just functions. Now, what about a piecewise function? What limit would I ask you about? Like, would I ask you what is the limit as x approaches 5? Hopefully you're like, maybe, but it's not interesting. Why is it interesting? Because x approaches 5 would always be bigger than 3, and you just use this bottom piece for both, and you get 7, and you get the function value 7, you get the limit that equals 7. Boring. What is the interesting part, the interesting x value, where all of a sudden, like, we could have, what's a jump? Like, what is that location? That location's 3. Because to the left of 3, I use this guy, but to the right of 3, I use that guy. Now, we are just checking limits right here. Do we have to worry? So, and we're looking and understanding that this is going to be a jump. Do we have to worry about holes or asymptotes? This is a very important question. Do we have to worry about a hole or an asymptote? The answer is no. There's no denominator that could possibly equal 0. We just have to worry about, does this piece meet up with this piece, or does this one-sided limit equal the other one-sided limit? Now we got like cicadas who just like popped up out of nowhere. They just like were like, yo, what's up? Cicada life, and now they're done. This has just been a really weird noise day. If I plug in 2.999, I'd plug into the top guy. I'd get something close to it if I plugged in 3, which I get 9 minus 5, which is 4. Left-hand limit. Let's look at the right-hand limit. If I plugged in 3.001, I'd plug it into something down here. 3.001 plus 2 is 5. This left-hand limit does not equal this right-hand limit. Therefore, this limit does not exist. What happens when limits don't exist? You have jumps or vertical asymptotes. What do you think this is? A vertical asymptote or a jump? It's a jump. Cool. What are other situations? Now, here's another jump right here. You need to understand that even though you get 0 over 0, this is the jump function. Why is it a jump function? Well, if I looked at the limit as x approaches 4 from the left of this function, we realize I'd get a positive number divided by the same number. Alzaga, were you looking for me? Cool. All right. Positive number, negative number, same number, -1. If I look to the right of 4, anywhere to the right of 4, this is the only like expression that could possibly jump. We get a positive number divided by itself, we get +1. Since the left-hand limit and the right-hand limit end up not agreeing, the limit doesn't exist, and we don't have like a vertical asymptote with a number over 0, jumps. Cool. This is one of those situations with the pointwise functions where it's like, hey, use this function for everywhere except for at 1 and at 2, we want to use these 2 points. Well, the situation could be that like I have a hole at 1, maybe I have a hole at 2, and maybe I have a point somewhere else, like maybe this point somewhere else. But guys, maybe I have that point smack dab on top of the first point. And all of a sudden, what was a hole is now like nothing to worry about. The hole got removed. That's why they call it removable discontinuity. Maybe we have a situation where at 2, we actually have a vertical asymptote, which means having a point somewhere over 2, 2 comma negative fourth, it's not going to do anything. This is the type of analysis we're going to do where it's like we could have holes and points above holes. This is why we're paying attention to these 2 values at 1 and 2, but this one everywhere else. So I'm just going to go ahead and analyze this guy like it was one of the questions that we started with. What are the interesting locations of this expression? Well, I see x equals 1 and x equals 2 are the interesting locations where the denominator could equal 0. I then do a little bit of work, and it's like, well, what would you get if you plugged in values close to 1? Well, this would be close to 0. This would be close to 0. These 2 factors would cancel, and you'd end up with just like 1 over 1 minus 2. If you cancel these, they get replaced by 1s. So I get negative 1. Let me just write this out. The limit as x approaches 1 of canceling 1 over x minus 2. 1 over 1 minus 2 is 1 over negative 1. I get negative 1. Okay, so we do have a limit. We're able to plug in 1. We're able to get a value after we canceled out those factors close to 0. So this is a removable discontinuity, and here's the location, 1 comma negative 1. Cool. Now let's look at x equals 2. Well, if I do the limit as x approaches 2, well, if I cancel, I'm still going to get a 0 in the denominator if I plug in 2 here. I don't have a 0 in the top and the bottom. It's just a 0 in the bottom. I'm not able to remove it, so this is non-removable. Infinite. All right, cool. Usually that's where we would be done, and we'd say, everything's good. I'm done. I got removable discontinuity at 1. I got a non-removable discontinuity at 2. But wait, there's more. I was actually told, guys, at 1, don't use this function. Use the point negative 1. At 2, don't use this function. Use the point negative 1/4. Well, guess what's happening? This point removes the removable discontinuity. It removes the location of this hole. This is very tough for a lot of students to understand. But this function up at the top, this expression, if I graphed it, at 1, x equals 1, it would have a location of negative 1 of a hole. At 2, it would have a vertical asymptote, a non-removable discontinuity. Okay, so that's just the top guy. That's just the x minus 1, x squared minus 3x plus 2. That's just the top guy. But these 2 points we would have to fit in. Well, the first point is 1, negative 1. Look at that. That point fills in the hole. The second point is 2, negative 1/4. That point does nothing. It does not remove the non-removable discontinuity. So what is our final answer? You're probably all waiting. Well, guess what? X equals 1, which we thought was a removable discontinuity, turns out got removed. We don't have to worry about it at all. We just have to worry about that discontinuity. Isn't that cool? Yeah, I can tell. Now, I'm going to do this question first, but then I'm also going to do something else. Like, let's pretend this A wasn't there. These questions say we want to make sure the function is continuous. Find A or B to ensure the function is continuous. What kind of function is this? It's a piecewise function. What is the interesting location of a piecewise function? Well, the location where we have a left-hand limit using one piece and a right-hand limit using the other piece. You should just immediately be like, yo, -1 is our important point. Let's just bring this back. Mr. Master would have asked us last class about the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. Definitely would have been questions, right? And you're like, okay, 1 from the left is like 0.999. Okay, Mr. Master's trying to be tricky. This is less than or equal to -1, so I would use this piece. Now I'm going to use it for x. Great. So if I plug in 0.999 for x, I essentially get a times 1 plus 3. Cool. And if I looked at 1 from the right, I'm thinking 1.001. Okay, -1. Whoops. Okay. So I got -1 from the left. I got -1 from the right. Be careful about -1 from the left. That's like -1.001. That's less than -1, and we're still going to be less than -1. So you would have a times -1 plus 3. That's the bottom piece. And then -0.9999, that value is bigger than -1. This is bigger than -1. I would plug it in here. Okay, if I plugged it in there, I would get a times -1 squared minus 2. I'd get a minus 2. Cool. What the heck does this mean? Well, guys, I want to make sure that the function is continuous. What happens with pieces? If the limits are different, we jump. But if, like at this situation, at -1, if I plugged in -1 to this, I got 1. If I plugged in -1 to this, I got 1. This limit exists. What does that look like? The pieces connecting. When the y values, or the left and the right-hand limit, matches, then we connect. And we connect, we're continuous. We need the pieces to connect. We need the limits to equal each other. We need this to equal this. We need the left-hand limit and the right-hand limit to approach the same y value so that the pieces connect. Now we just have to solve this equation. I'm going to add 2. I'm going to add an a. I get 2a equals 5. I get a equals 5/2. Do you have to do all this work and show all that? No. But I'm going to, because I want you to see that it's just like last class, only you understand the important points that you need to check. Okay, we got 2 important points, 1 and 3, which means we have 4 total limits we need to evaluate. We need the limit as x approaches 1 from the left. We need the limit as x approaches 1 from the right. Those better equal each other. 1 from the left, 0.999, plugging into the top guy. I get 2. I'm not going to show like x plus 1 equals 2, but I can. 1 from the right, 1.001. I'm only plugging that into here. 1.001 is bigger than 1, but it's less than 3. If I plug it in, I get a times 1 plus b. Cool. These need to equal each other for the 2 pieces to meet up with each other. What about the other situation? Well, we have to have the limit as x approaches 3 from the left equal the limit as x approaches 3 from the right, or else we would have a jump. We don't want jumps. We want to ensure the function is continuous. Three from the left, 2.999 falls in here. Using that 2.999, it's like plugging in 3. I get 3a plus b. A times 3 plus B. 3 from the right, 3.001. That's right there. Plug it in here. We get 0. Cool. 3.001 times negative 2 plus 6 is 0. Okay. These two limits need to equal so that our pieces connect. So we get 3a plus b equals 0. What do we do now? I got one equation with a's and b's. I have another equation with a's and b's. Do you remember how to solve systems of equations? Some of you probably like, oh yeah, sure. Some of you are like, what? Substitution's always our friend. Solve for a variable, substitute in the other equation. That way we just have one variable that we can solve for, et cetera, go from there. So you could also stack them on top of each other and add to eliminate. But I'm just going to start with this. I'm going to subtract A, and I get that B equals 2 minus A. I solve for B because I just have one of these B's. I'm going to take B equals 2 minus A and plug it in there. And let's see what we got. 3a plus 2 minus a equals 0. So 2 plus 2a equals 0. A's got to equal negative 1. Once you get that a is negative 1, substitute it back in into either equation to get b must be 3. Having a being that number and having b being that number will ensure this entire function is continuous. It doesn't have jumps, it being a piecewise function. Okay, more of the same. Honestly, I did not have to give you like that A right there. Like that did not have to be there. I could have just given you an A in one of them. It's like, what does this have to be? You know, you don't need it in both places. I think I gave it to you in both places just so you're solving equations that are a little bit more difficult than just like one or two steps. What is the important point? Where the limits will be using two different functions. 0 is important. We would look to the left and right of 0. Here, if I'm using that, I'd get the cosine of 0 plus a, which is 1 plus a. If I'm using this, I would use x minus 4a, which would give us negative 4a. To have this function be continuous, the left-hand limit and the right-hand limit need to meet up with each other, agree with each other, set them equal to each other. Subtract a, negative 5a, I get a is negative 1/5. Same one as above. I'm going to show all the work. You do not have to. Just get the right answer. We'll worry about showing work more in the second semester when we switch over to free response. This has to equal this. It's nice we already have something solved for. Getting 2 from the left, I'm going to use the middle one. Using 2 from the right, I'm going to use the bottom one. These need to equal each other. For them to meet up. I'm going to be able to solve for b here. So this is not necessarily a system. We got b is 3. Substitute back in. We get a is 5. Once it's ready. Okay, a couple more. Again, I don't have to give you a's in both. It's just like, so you have to solve an equation. We see the important point where we're going to have different equations used for the different one-sided limits. If I used any other point, like 3, 1, 0, you would only use the top equation or only use the bottom equation. To the left would use x squared minus 3a. To the right would be x cubed minus a. This would be 4 minus 3a. This would be 8 minus a. These need to equal each other for the two pieces to meet up. 2a equals negative 4. A equals negative 2. 4 plus 6 is 10. 8 minus negative 2 is 10. All right, negative 1, left and right. Two to the negative first. Ooh, what's 2 to the negative first? Powers 2 cubed is 2 times 2 times 2. The way I like to remember is 2 to the negative power is like instead of multiplying, it's dividing. Divide by 2, divide by 2, divide by 2 would be 2 to the negative third. There's a rule where it's like, oh, you just flip it and make the power positive. But that's the idea behind like negative powers is to divide instead of multiply. So we just get 2. If I were to go to the right of negative 1, I would use ax plus 2b, and I'd get negative a plus 2b, giving us this equation. 2 has to equal negative a plus 2b. If I were to use 2 on the left, I would use 2x, ax plus 2b, giving me 2a plus 2b. If I were to use 2 to the right, I would use 3 to the x minus 2, which would give me 9 minus 2, which is 7. This stinks. Probably a little bit too complicated. I mean, it's not too complicated, it's just annoying. I'm going to solve for a here. That's probably the easiest one to solve for. If I solve for a, I get 2b minus 2. I will substitute in that. I substituted in for a. I got 2 times 2b minus 2. I now can distribute, solve. It's not going to be pretty. Whatever. Oh, gross. B's 11.6. You got to be able to work with fractions, guys, even though you don't want to. And I don't want to, but I'm going to. 2 equals, well, I already have a. A is 2b minus 2. So a is 2b minus 2. So 2 times 11.6 minus 2. It's 22.6, which is 11 thirds. 11 thirds minus 2. Is 11 thirds minus 6 thirds, which is 5 thirds. You'll have fractions sometimes, but most of your quiz questions, the numbers are fine. I mean, like, the numbers aren't crazy fractions that take a bunch to get. Okay. Do you really understand what's going on? Let's find out. This is one of those use that guy for everything except for one point. And at that point, use this value. Okay. Since we're using this for everywhere, we might as well analyze this. And when I analyze this, I realize, oh, 2 is a discontinuity because it makes the bottom 0. At 2, however, by examining the limit, you realize you can remove the whole like factors of 0. You realize you have a 0 over 0. You get 4. What does that mean? Yo, this has a removable discontinuity. It's got a hole. The hole is located at 2, 4. For the function to be continuous, we got to have a function value of 4 when x is 2. Right now, we just have a limit, but we don't have a function value. The function value comes from here. When x is 2, this needs to equal 4. So we kind of figure out what f of 2 has to be, because we get the limit, that's 4, but when I plug in just 2, I would plug it into the bottom piece, and I get 6 plus b. Okay, that function value of 6 plus b has to equal 4. B's got to be -2 for that to be true. We make sure the limit and the function value agree with each other. So we don't have a hole, we're continuous. We have a point filling in the hole. Try to do that with this one. Go. Don't just copy down. Let's analyze this. Realize x equals -3 is an interesting point where we don't have a function value because the denominator is equal to 0. Let's look at the limit. As x approaches -3, realize we do have a limit because this function value close to 0. The noises today are just out of control. We just had like a couple like drilling over there. We got the bros on the lawnmower just driving around. This is great. If I were to plug in something close to -3, this number close to 0 would cancel with this number close to 0, give us a value of -1. This means I have a removable discontinuity. I have a hole, because holes have limits. The hole's location is -3, -1. Cool? That's a y coordinate location. For this function to be continuous, the function value needs to agree with the limit. If I plugged in -3, exactly at -3, that better equal the location of the hole. Well, I get -3 minus a. So funny. So funny. I can't wait. I should have been in a classroom right now. -3 minus a better be the same as that limit for the limit and the function value to agree with each other. Get a equals -2. Finishing up with the intermediate value theorem, which we didn't get to in period 2, and I apologize. It's actually very easy, and I'm not gonna stress you out about it for the quiz. Like, there's something intuitive that uses the intermediate value theorem on the test, but since it's multiple choice, it's actually pretty easy. The intermediate value theorem is just a continuity theorem. It says, if you know 2 distinct points on a function, and you know that your function is continuous between those 2 points, that you connect those 2 points, well, you are guaranteed to have a point with an x value that will produce a y value in between that. Or if you know this is the point 1, -2, and this is the point 3, 1, you know that this function has some x value that has to be between 1 and 3 that will produce the y value of any y value between -1 and 2. So like you have the point 1, -2. Start over. I don't like to reuse numbers. 1, -2. Let's use 3, 4. You have these 2 points. You'll write it down over here. Since you have the point, 1, -2, 3, 4. There's guaranteed to be an x value between 1 and 3 that produces any y value between -2 and 4. Pick a y value. Oh, 0. Yeah. If we connect these two things and we don't like have a jump or an asymptote or a hole, we're guaranteed to cross through the y coordinate 0. Oh, what about the y coordinate of 1? Yeah, sure. There's going to be some x value that will produce the y value of 1. What is the x value? We don't know. We don't care about what the x value is. We just know it exists. This is we are guaranteed to have a solution theorem, not necessarily knowing what the solution is. This is the most common example that I'm going to give you. This is what's going to be on your quiz that I'll give you I won't give you for the quiz, just so you know, but it will be on the test, something like this. Cool. Show that there's a solution to f of x equals 4. Show that this can equal 4. Well, many of you are like, okay, let's try to solve. It's like, no, don't bother solving. It's something that you can't solve by hand. So don't do it. Instead, what you want to do to show that there is, not show what is it, show that there just exists, is the following. Tell me if this function is continuous. I say yes, it's continuous. Why is it continuous? Because there's no denominator. It can never have a denominator equal to 0 situation. Okay, step 1. Step 2, give me 2 function values. What are the 2 function values? I don't know. Pick 2 random ones, or if they give you an interval, pick the ends of the intervals. If I plug in 0, I get -2. I get 27 minus 9 plus 3 minus 2. So that's 18 plus 2, which is 20. Yo, there's got to be an x. What is it? Not sure. That will produce the y value of 40. The x is between 0 and 3. The y value, 4, is between -2 and 20, which is why I know this works. This is all you need to show. Done. Okay? All you need to do, guys, is tell me that the function's continuous. Give me 2 points. Use the interval to help. 8 minus 12 plus 3 is -1. 27 minus 27 plus 3. Now, because you are connecting these points, 2, -1, and 3, 3, you know that you're connecting smoothly. You know you have to pass through 0. That's what it means to have a root. It means it's a 0. I'm guaranteed to have some x value between 2 and 3 that will produce the y value of 0. You're done. As long as you show that the function is continuous, doesn't have a denominator, doesn't have any jumps, then we're good. Show that f of x equals pi at least once. Man, I didn't give you an interval. All right, well, let's work with something. I got 1. Let's plug in 3. E cubed plus 9. Do you think that's bigger than pi? Yeah, it is. So you know that there's no denominator. The function's continuous. There's got to be an x value, at least between 0 and 3. I could even do 0 and 1 because I know e plus 1 is 3.7 versus 3.1. But whatever, shows that you have at least one solution. There you go. Because pi is between those two numbers. You could have also say, since the function is continuous, We can even make a smaller guy. E plus 1 is bigger than pi. Pi is in between 1 and e plus 1. If you don't know that e is 2.7, it's no big deal. That's the intermediate value theorem, which we didn't get to in period 2, but honestly, it's not a big deal. It's the continuity theorem. It shows the existence of solutions. Not a huge deal. What's a big deal is remembering and understanding the questions that we are asking here are really just the same as the questions from day 1, with 2 new things. One thing, understanding vertical asymptotes, numbers over 0, okay? The limit doesn't exist of vertical asymptotes. The other thing is understanding what are the important points that, like, I asked you the limit questions about. The possible locations of jumps, the possible undefined function value locations. You have to figure that out, whether you look at a piecewise function where the one-sided limits use 2 different functions, or where we use an expression where the denominator equals 0. So I hope this is clear. It's really day 1, guys. It's really just a bunch of limit questions, but you figure out the number that's important. And we're good. Okay? All right, I hope this saves. I'll see you guys tomorrow. Peace.